Again, so if you have a positive definite, a bilinear form in this case, this is equivalent to actually minimizing over all possible w's, a w w half plus b w, right? This is equivalent. Yes.
If you put a minus for the a, you don't do that.
So here we are saying if u is so let me actually write a little bit clearer here. So if you have a of uv plus b of v equal to 0, and that turns out to be a maximization problem, right? On the other hand, if you have a minus in a, you easily convert that into a of wv minus b of v equal to 0, right? So that turns out to be a minimization problem of half of a wv minus, minimization of a ww minus bw. So it depends on, right? So it depends on a being positive definite or negative definite. So the convention is really, the canonical form is to make a positive definite and also change the sign of the equation so that a is positive in the equation, which turns out to be a minimization problem. Yes? Oh, yeah, okay, so let me actually explain why do we, for example, let me explain over here, right? So why can we translate the weak form into the minimization problem? That's because if you take a small variation in this, let's say, let me call this j, the objective function. If you take a small variation in w, the resulting variation in j is going to be half of a w delta w, right, plus half of a delta w plus b of delta w, right? So these are basically, I'm using the linearity of a in both the first variable and the second variable, also the linearity of b. Okay, so the a being symmetric like this makes these two terms combine into a of w and delta w plus b of delta w. So the w being an optimal means when you make a small variation, the objective function is not changed to first order, right? If you make an infinitesimal variation, the resulting change in objective function is equal to 0. So the first, this is the first order optimality condition for any optimization problem, right? Basically the derivative at the optimal is going to be 0. If it's a variation optimization problem, the equivalent thing to the derivative being 0 is the variation being 0. So this is this for any delta w, right? So this is basically the same as saying the weak form is true for any v, satisfying the boundary condition. Okay? Yes?
Why is it necessary to perform the integration by parts one more time? The first time you do it, is that not by linear?
So actually, even without I doing it, it's already bilinear. But it is not symmetric, nor it is positive definite, right? So basically, all this manipulation is to make it symmetric and positive definite. Okay, another consequence of this manipulation is to make the equation weaker. So basically, this equation, right, saying that for any possible variation v, the weak form holds, is in some sense equivalent to the original differential equation, fourth order derivative of w plus f equal to 0. But it's only equivalent in one way, but not the other. Which means if this equation, if the strong form of the equation is satisfied, I mean, it's similar to our finite volume, right? In finite volume, if the primitive form is satisfied, then the integral form is also satisfied. But the integral form being satisfied doesn't mean the primitive form being satisfied, because the integral form can be satisfied by discontinuous solutions. Here it's similar, except for it's similar that the weak form is weaker than the strong form, than the differential form. Except for it's weaker in a different sense. So can somebody actually take a look and figure out, compare this equation and this equation to see in what sense is the weak form weaker than the strong form? Yes? Yes, it actually requires less derivatives. The strong form only makes sense if my solution W is actually fourth order differentiable. While the weak form only requires my function to be second order differentiable. Right? So actually it requires less smoothness from my solution. Okay, this actually is pretty important when you actually, for example, if you look back into the Poisson's equation. The Poisson's equation requires W to be second order differentiable. Okay? And the weak form only requires W to be first order differentiable, to have a derivative, but doesn't require me to have a, actually it doesn't even require me to have a derivative everywhere. It just requires me to have a derivative almost everywhere, because I just need to integrate over the derivative, right? So if, for example, I have a W that is like this. So let me give an example. If I have a solution to Poisson's equation, let's say 0 and 1 are both equal to 0, but the solution is like this. It makes no sense to be the solution to the strong form of the Poisson's equation, because, well, the second order derivative is 0. Is 0 here, and it's not defined at the sharp corner, right? And this doesn't make sense to be the solution of Poisson's equation. Well, if you look at the weak form, it actually does make a lot of sense. The derivative, the first order derivative of the solution W, of this function W to x, is actually a positive number on the left and the negative number on the right. And then if you examine closely, it is actually the Poisson's the solution to the Poisson's equation if f is a delta function, right? So the Poisson's equation, in some sense, is like, in 1D, it's like an elastic string. And if you put a point force over here, so if f is like this, you actually get a solution like that. So this is a mathematically perfect valid solution of the weak form, but doesn't really make that much sense in the strong form. Okay. Any questions? That's basically why the weak form is called the weak form.